This is going to be a technical introduction to the PSF file pin service. Just a little while ago I published this video to YouTube, which is a short demonstration of the user interface. This second video is going to go a little more in depth into the back end and the system that is used to pin these files. And the audience that should be interested in this video are other PSF developers who are interested in contributing and possibly running back-end services, because what will eventually be made, and I'll get into this on the last slide when I talk about the roadmap, is the Permissionless Software Foundation, the PSF, is going to create bounties to pay people to run these back ends and thereby create a decentralized infrastructure. So I want to go in a bit onto the technical side of things, what's happening under the hood beyond just the simple user interface that I demoed in the last video. So this is the system diagram and it's actually a lot simpler than it looks. Let me walk through this. So what I demoed in the video was the user interface, the web app at upload.psfoundation.info. So that's what I demoed here. That's what this box is. It talks to a Node.js application that is basically a server. And the important thing about this block is that this is going to go away. It was just easier to code up the prototype this way, but all this functionality that's in this block will eventually be merged into the web app, so there will be no back end. It'll just be a front end application talking directly to a cache stack. There are multiple implementations of the cache stack, so there's not one cache stack that it talks to. So this back end is decentralized as well. I make an effort to decentralize everything. That's part of why this is technically complex. Is it's much harder to build decentralized systems than it is to build centralized systems. And this is a fully decentralized system, or at least it will be. That's the vision for it. So what it does is that UI, when it talks to this back end, and again this functionality will be pulled into the front end, it generates two transactions. The first onto the blockchain. And the first transaction is called a proof of burn, and that's essentially a proof of payment. It burns a set amount of PSF tokens to pay for the file hosting, and the result is a transaction or a transaction ID, and that's known as the proof of burn, that transaction ID. It's proof that you burned the tokens and that therefore paid and therefore have a right to have the system pin the files. The second transaction that it creates is called a claim, and I'll go into that in a bit more in a minute, but it essentially, that has the file information along with the proof of burn transaction. So those two transactions get written to the blockchain, and then they get picked up by the PSF SLP indexer, and that is an indexer that was developed by the Permissionless Software Foundation to track SLP tokens. It's a core piece of the cache stack. And what an indexer is, if you're unfamiliar with it, it's kind of like a search engine. Whereas a search engine crawls the internet, an indexer crawls the blockchain. And so it pulls out metadata from the transaction data that's not like obviously available and stitches it together into something that's a little more obviously available, and in the sense of like SLP tokens. That's how it works. So I modified this indexer, so not only is it tracking SLP tokens, it also tracks these pin claims, which is the information about, hey, here's a file and I want it to be pinned on the IPFS network, and here's my proof of payment. So everything is contained in that claim transaction. So when the indexer detects one of these transactions on the blockchain, it triggers this IPFS file pin service with a webhook. And so this gets triggered, and this IPFS file pin service, this has an IPFS node embedded in it, which is a Helia, which is the new JavaScript implementation of IPFS. And so when this is notified by the indexer that it's found a new pin claim on the blockchain, this IPFS file pin service will validate the transaction, make sure that it meets all the rules for a valid transaction, and if it is valid, it will download the file over IPFS and pin it. And so the idea is for there to be 3 or more instances of this IPFS file pin service out there on the internet. That's what we're going to create bounties for, and then it will be a truly decentralized file hosting. Each node, each instance out there will independently validate each transaction and pin the file, and so there'll be redundant pinning of the file on the internet. And so that will make it decentralized and also have high uptime for the file hosting. And then this block also uses the cache stack. So there's this cache stack block and this cache stack block. That's just pointing out that the system on the left and the system on the right, they communicate through the blockchain, and they both depend on the cache stack, which is a important component that the PSF built. So let me go through each element here and show you where the code is and talk about it a little bit more in depth, and I'll also show you some of these transactions. So like I said, the PWB image upload, that's going to be renamed because we're actually not using the pay-to-write database anymore. We're using the blockchain instead of a database. And it's just a React web app user interface. The code is here. So all of this code is on GitHub under the Permissionless Software Foundation GitHub group. And then the repository is named exactly what's here in the slides. So this is the React image upload directory, and then this is the back end. It also lives in the same GitHub group. It's just same name, just with dash backend. So this is a Node.js web server, and the UI talks to it directly. So these are intended to be run, on a web server. Although eventually, like I said, this functionality will get merged into the front end, and then the front end can actually be stored using this exact same file pinning service, so that the front end can be retrieved over IPFS and not have some dedicated URL that can be blocked or censored. So yeah, this back end though is what's actually creating the transactions and writing it to the blockchain. Then there's the cache stack, and if you're unfamiliar with the cache stack, it's at cachestack.info, and this is a complicated diagram of the system, but essentially what it is it's a REST API that talks to the blockchain and to a couple other indexers. And so if you're a web developer, it's a very handy system because all you have to do is talk to one REST API, which is very normal in the web development world, and then you can interact with the blockchain and all these other indexers like the token indexer. And then there's the PSF SLP indexer. That's our token indexer, and it crawls the blockchain. And there is a branch called pin IPFS, and that's the branch that is running this. The master branch only tracks SLP tokens. The pin IPFS branch tracks SLP tokens, and it also tracks these pin claims. So if you want to run this infrastructure yourself, this is the branch you want to be on. And it's also, there's a Docker container for it. And then finally there is this IPFS file pin service, which again is a Node.js web server. It's got the Helia IPFS node embedded in it, and so it validates these transactions and then ultimately pins the files and makes them available for download. So let me show, I said there's these two transactions. There's a proof of burn transaction, and then there's a pin claim transaction. So let me actually walk through this. A proof of burn is just a normal SLP transaction. It's no different than any other transaction. If it's different in any way, it's the inputs are less than the outputs, and this is what's known as a controlled burn. This is how you intentionally burn SLP tokens. So here's an example of a transaction that was used. So I had an input of 2 point whatever tokens, and I had an output of 1.9 tokens, and so the difference here is 0.08, and that is how much was burned, how many tokens was burned in this transaction. So the transaction itself, this transaction ID, is the proof of burn. The transaction ID is the proof of burn. And so it's just a transaction where some tokens were burned. The quantity of tokens that need to be burned are set by the PSF Minting Council. That's a decentralized group with a multi-sig wallet, and they periodically update the cost to pin a file. And so right now, and they're trying to target 1 penny per megabyte, and that's the goal. And so crypto prices, they fluctuate, so it's never perfectly where it is, but the Minting Council comes together every few months, and they use their multi-sig wallet to update the cost of writing so that it's approximately 1 penny per megabyte, and so that's what the price is right now. So this number will change to reflect changing prices in cryptocurrencies, but it's always going to target approximately 1 penny per megabyte in US dollars. So that's all that's going on here. So the simple way to think about this is a proof of burn is just a transaction ID for a transaction that burned some tokens. And then the pin claim is a new idea. This is actually based on a specification I wrote about a year ago on this idea of claims, and this was an idea that was born from Vitalik's Buterin's idea of soul-bound tokens. And so all a claim is it's just a normal transaction with an op return, and there's some data in that op return, and there's I could go deeper into like non-repudiation and signed messages and all that stuff, but effectively it's just a transaction on the blockchain. And the op return, here is the transaction, and here is the op return data, and it has 4 parts. It's actually easier if I show you here in the code. So the first part of the op return has these 4 bytes, and this is hexadecimal representation. This is known as a low-cat ID, and this is simply an identifier so that indexers who find this transaction, or the purpose of a low-cat ID in general, is that so an indexer can quickly identify sort of what category of application this transaction belongs to. So SLP tokens have a low-cat ID, and this is a low-cat ID. There's a spreadsheet on GitHub that lists all the different applications and the low-cat ID that they've reserved. This is the low-cat ID that I'm reserving for this application. So that's the first 4 bytes of the op return, and it's in hex, so it doesn't really translate very well into ASCII. And then the next part is the proof of burn transaction ID. So it's just this transaction ID right here, but converted into binary. So that's why it looks all garbled and weird here. It's by putting it into binary, it saves space, about 50% space. And then the third part is the CID. So this is the fingerprint that is used to identify the file on the IPFS network. This is the thing we're actually pinning. I mean, we're pinning the file, but it's identified by a CID. So that's in clear text, and that can be seen here. These CIDs typically start with BAF. So that's the CID right there. And then lastly, this fourth part is the file name, because when a file is converted to a CID, it loses the file name info. So this was the name of the file, and so that's what the op return looks like, and that's how you sort of parse it visually. But that's all a pin claim is. It's just a transaction with an op return, and it's has these specific 4 parts. So that's all a pin claim is. And so those are those 2 transactions. And so the IPFS file pin service, so the indexer detects these transactions, and specifically it detects the pin claim because the pin claim has the proof of burn transaction in its op return. So it's just that one transaction. The pin claim is detected by the indexer, triggers the IPFS file pin service with a webhook, And then the IPFS file pin service, it retrieves both those transactions. It retrieves the pin claim, and then it from the full node, so all the transaction data, and then it parses the op return and gets the proof of burn transaction ID, and then gets the proof of burn transaction, and then it verifies that, you know, yes, enough PSF tokens were burned. Yes, the same person who burned the tokens is the same person who created the pin claim, and then if everything checks out, it will use that CID to retrieve the file over IPFS and then pin it in its own hard drive. And so that's how the system works. So in terms of roadmap, this is very new. I just published these videos because I finally have a working prototype, and what I'm hoping to do is encourage other developers associated with the Permissionless Software Foundation to collaborate with me, and at the very least look forward to running some infrastructure and possibly getting in on some of these bounties that we're going to create. So in terms of a roadmap and moving forward from here, all those system blocks that I showed you, I want to get them back up to 100% unit test coverage. They're all written in JavaScript, and I like maintaining my projects at 100% unit test coverage. It makes it much easier to collaborate with other people, and also gives us the confidence to add new features without worrying that we're breaking old features. So I want to get them all back up to 100% unit test coverage and get the system working reliably in the limited functionality that it is now. And then the second most pressing thing that I need to do is that the user interface is very buggy. It really only works on that happy path, and it has little to no error handling at the moment. So it needs to have much better error handling, and that'll just make it easier for people to use the app. And then actually, I guess from there, I want to increase file limit from 1 megabyte to 100 megabytes. So currently it will only work for files under a megabyte. That's just to protect the system. But the goal is to get this up so you can store up to 100 megabytes, because that would let people upload video. It would let people upload whole web apps, so we can have a decentralized front ends for, like, say, DeFi backends. That's the real one of the main objectives I'm trying to achieve with this, and so that would be a big goal. And then I need to create a monitoring system that just so that can find these it's a decentralized system, so there's going to be multiple instances of this file pinning service. So the idea behind the monitoring system is to find them and monitor them and tell when they're down, because that'll be an important part of the bounty system. We'll only reward people who can keep their systems up and functioning over a period of time, like a month. And so this will be critical to develop before the bounties. And then I'll create a series of videos like this showing how to set up all the infrastructure. I already have videos at cachestack.info on how to set up the cache stack. That's the bulk of the work. So it would really just be in-depth videos showing how to set up the file pin service and the front end. And then finally, the PSF can launch a bounty program to reimburse people for running this infrastructure. And then it'll be a fully decentralized system that's generating cash flow as people burn PSF tokens to host their files. That will increase the price of the PSF token, and then that makes the PSF token valuable so that the foundation can pay the people who are running the infrastructure for those bounties, and then they can do whatever they want. That gives the token value so that those people can actually cash out and pay their bills with the token. So it creates a circular economy. So that's really the big goal I'm trying to do. Like all of this, I'm trying to achieve personally. I'm trying to achieve multiple goals here. Like one is to create a truly decentralized file hosting service that's censorship resistant and permissionless. And the second is to create a DAO with a circular economy that's providing services, and then those services are going back into funding the development of those services. So that's the roadmap. That's where we're going from here.